morning, students. We'll be learning the second part of the chapter. This is known as magnetic effect of current. Magnetic effect of electric current. It was first discovered by Hans Christian Ørsted. He was a Danish scientist and he only explored the relationship between electric current and magnetism. Current is the flow of electrons, and this is how we harness electricity. Ørsted conducted one experiment by bringing a compass needle near a current carrying conductor. He discovered that the compass needle got deflected when electric current passed through the conductor and was able to infer a relationship between the electric current and magnet. The experiment is shown in the diagram. One magnetic needle is kept and a current carrying conductor is kept above it, and this wire is connected to a battery through switch. So when current is passing through the conductor, the magnetic needle showed a kind of deflection. In the second figure, we have seen that the polarity of the battery is changed, so the direction of current is also reversed. And it was observed that the deflection of magnetic needle was also reversed. Let us do an activity on magnetic effect of current. We are taking a cardboard and making a hole at the center of it. We place the cardboard horizontally, and through the hole a straight conducting wire is inserted. The two ends of the wire is connected to a battery through a switch. When the circuit is closed, current started passing through it, and at that point we are sprinkling some iron filings on the cardboard, and we tap the cardboard gently. It will be seen that concentric circles of iron filings are formed as it is shown in the figure, and through the common center of the concentric circles the conducting wire is passing. Now if we place a small needle magnet on the concentric circles, we will see the magnetic needle, north pole of the magnetic needle will point to a particular direction, and in that direction the arrows are drawn as it is shown in the second figure. Now we are changing the polarity of the battery as shown in the third figure. So the direction of current is also reversed. Look at it. In the second diagram, the current was flowing in downward direction and the arrows are in clockwise direction. Arrows of the magnetic field is in clockwise direction. In the third figure, the polarity of battery is changed, so the current is reversed. Initially it was downwards, now the current is flowing in the upward direction. And if I now place the same magnetic needle on the cardboard, we will see the magnetic north pole will be deflected in opposite direction. So when the current was downwards, magnetic needle was showing clockwise direction, and when the current is upwards, magnetic needle was showing anti-clockwise direction. So one inference can be drawn that when the direction of current is reversed, the magnetic field direction is also reversed. Now what is the contribution of Ørsted? He discovered that electricity and magnetism are linked to each other, and it is proved when an electric current passes through the copper wire, it produces a magnetic effect. The magnetic effect of electric current is known as electromagnetic effect. His inventions and research work later helped in creating technologies such as radio, television, fiber optics, etc. The same activity is shown through a diagram, and here we are showing the direction of magnetic field through right hand thumb rule. Now, right hand thumb rule states that if we hold a conductor with right hand and stretch the thumb in the direction of current, then other fingers will curl around in the direction of magnetic field, which is shown here, that the current is downward direction and the other fingers are showing clockwise direction. Here the statement of right hand thumb rule is given. You have to remember the statement, and several diagrams are given. Every diagram is explaining right hand thumb rule. In all the diagrams you notice that the right hand is holding the conducting wire and the thumb is pointing towards the current. It is shown by arrow in each diagram, and the other fingers are curling towards the direction of magnetic field. So, whatever be the orientation of the conducting wire, the thumb of right hand will also be pointed towards it. Characteristics of magnetic field lines due to current carrying straight conductor. The magnetic field lines produced due to a current carrying conductor has the following characteristics. Magnetic field lines encircle the conductor. It lies in a plane perpendicular to the conductor or the direction of flow of current. When the direction of flow of current is reversed, the direction of magnetic field also gets reversed. The strength of the field is directly proportional to the magnitude of current. More is the current, more will be the strength of magnetic field. Strength of the field at any point is inversely proportional to the distance of the point from the wire. More is the distance, less will be the magnetic strength. Now we will discuss about one more activity. We are taking once again a cardboard and placing it horizontally. This time, instead of one hole, we are making two holes at a distance apart. We are inserting two conducting wires, straight conducting wires through two holes and placing the cardboard once again horizontally. Now, the two open ends of the straight conductors are bent and they are joined together to form a semicircle, and the lower ends also, they are bent and they are connected to a battery through a switch. Now it is looking like the two wires, when they are joined, they are looking like a circular loop. Now when the current is passed according to the polarity of the battery, from the left limb the current is moving in upward direction, and from the right limb the current is flowing in downward direction. See, if we apply right hand thumb rule on the left arm, we will see the thumb will be pointed in the upward direction and the other fingers will curl towards the direction, anti-clockwise direction. Similarly, if we apply right hand thumb rule on the right limb of the circular coil, then the thumb will be pointed downwards and the other fingers will be pointing in clockwise direction. So we can see in between the two limbs of the circular loop, the magnetic field lines are all moving inside the plane. That means it is going away from the observer. So all the lines are moving towards that direction. If we sprinkle iron filings and tap, automatically they will show concentric circles around the two limbs. And if you place a magnetic needle, the north pole of the magnetic needle will show in that direction, in the direction which is shown by the arrow in the diagram. So from the straight current carrying conductor, we are extending and we are applying the same concept in case of circular loop. Now, the same diagrams of magnetic field in a circular loop are shown in 3 different ways. The first diagram is taken from NCERT book. You can take this diagram and practice. And the other 2 diagrams are where the circular loop is kept vertically. In the third diagram, we have shown how right hand thumb rule is applied in the 2 limbs of circular coil, as it is discussed in the previous slide. The learning outcome of this exercise is, at the end of the class, students will be able to know magnetic effect of current as an inference of Oersted's experiment. They will be able to observe the magnetic field pattern around a straight current carrying conductor through an activity. They will be able to understand the concept of right hand thumb rule. They will be able to identify the direction of magnetic field lines around a straight current carrying conductor using right hand thumb rule. They will be able to observe the magnetic field pattern around a circular coil through an activity. They will also be able to identify the direction of magnetic field lines around a circular current carrying conductor using right hand thumb rule. Here is an experiential learning on the discussed concept. We are taking an iron nail and we are winding a conducting wire on it, and the 2 ends are connected to a battery. When the both ends are connected to battery positive and negative terminal, current will start flowing, and if we place some iron pins near it, it will start attracting. So from the concept of magnetic field around a circular loop, we are extending the concept, and there are many loops formed around the iron nail. So for each loop, the same type of magnetic field is produced during the passage of current. So the same concept of circular loop we are extending, and we are forming a solenoid, which we will be discussing in the next class. Here is some critical thinking questions. The first question is, when an electric current is passed through any wire, a magnetic field is produced around it. Then why an electric iron connecting cables does not attract nearby iron objects when the electric current is switched on through it? Why is it happening? Because the strength of magnetic field which is produced in the cable is very, very feeble and weak. So it cannot show that kind of effect. Now here is one more critical thinking question. One diagram is given and 2 magnets are there kept apart, and the first magnet, it is showing the north pole, and we know that the lines of force are emerging from north pole. So what you have to do, you have to redraw the diagram and label the poles. So in the second diagram, we can see that the lines are going out. It is also emerging from magnet 2 of that pole. So what is happening? That is also a north pole of the second magnet. Now we can see the second part of the question is asking which is the weaker magnet. We can see that the lines of force on the left hand side is actually trying to repel the lines of force on right hand side. So it is stronger. So the weaker field is produced by magnet 2. So magnet 2 is weaker one. I hope all of you understood the concept of magnetic effect of current. Thank you, children.